Welcome everybody to the Bell Museum. My name is Sarah Comprood. I'm the planetarium educator here. Over the past many years, we've actually had the privilege of working with the Minnesota Institute for Astrophysics on many different projects, and we are very happy to be hosting the third lecture of the Institute's public lecture series. And without further ado, because we're all here to talk about exoplanets, I am actually going to introduce Dr. Evan Skillman, the director of the Minnesota Institute for Astrophysics. Evan?
Thank you, Sarah. It's so good to see all of you here and that you're showing your enthusiasm for astrophysics with us. This public lecture, as Sarah said, is our third lecture. We're not going to do one next semester because we're going to do a Kaufmanis lecture next semester. And so in April, mark your calendars, and if you filled out things, we'll notify you for that. It's my extreme pleasure to introduce Chick Woodward today. One thing that's interesting is that Chick grew up in Rochester, New York, where I grew up. And Chick studied music at the Eastman School Preparatory School, and I studied there too. And Chick is a percussionist, and I studied percussion too. And you may have figured out by now that I am Chick's evil twin. It's just a coincidence that we're both on the same faculty here. But there's just so many great things to say about Chick. He's an expert in comets, in nova, in interstellar dust, in addition to all his great work that he does on exoplanets. He manages our connections with the Large Binocular Telescope in Arizona. He's done a lot of service within our community, both through serving on various telescope boards and working with various panels of the National Academy. And he's currently the vice president of the American Astronomical Society. He's just a tremendous asset for our faculty, and I'm very pleased that he agreed to give this talk for you this evening. So without further ado.
Well, great. Thank you, Evan, and welcome. Welcome. So, for about the next hour, I hope to take you on a fun trip. It's our voyage, as Virgil said in the Aeneid. It's us to the stars, and I hope to take you there a little bit. It's part of my journey. It's part of our journey, and hopefully it'll be part of your journey. This whole world of exoplanets. And my goal for tonight is to try to give you a little bit of feel for our understanding of exoplanets right now, some of the things that we've learned over the last 10 years, and some of the things that here at the University of Minnesota we're actively involved with large teams both domestically and internationally. Now, this whole idea of heading towards the stars, and this sort of image here is meant to sort of lull you into some passion about what these worlds might have, is not something new. I would point out to you that this vexing concept about worlds beyond the Earth has been gnawing at humankind and human inspiration and human curiosity now for thousands of years. Epicurus himself said there are infinite worlds, both like and unlike this world that we inhabit. And we must believe, perhaps, that on all worlds there are living creatures. And we'll come back to this idea a little bit later. Is there other life on other planets? Not only in our own solar system, but on those exoplanets that we see. And of course, the Epicureans are very famous for a whole lot of things, but they actually had a very interesting philosophy that imparts this drive for us to explore the cosmos. And that's what I hope to do with you tonight, is give you a little taste of this exploration. And in particular, our study and characterization and understanding about the myriad of worlds that we now see to exist around other stars other than our own sun. And one of the things that I would like to do is sort of lead you through a little bit of the logic about how we do this and where we begin to search. If you take a particular image of a nice star cluster at night, this is what the stars look like. And you might say to yourself, well, where do we start this hunt? Where do we start this exploration looking for other worlds? We start with looking at the stars and taking the knowledge that we have on our own planet and extending that out into space to try to project or expect what we might find. Indeed, what we do is we look at our own solar system, and on the left here is a very interesting picture that was taken by Voyager 1, one of the spacecraft that is your legacy. It's humankind's sort of signal to the cosmos that we're here. This spacecraft has left our solar system to fly forever in the cosmos, to perhaps be found at one point. But one of the interesting things that the Voyager did, in part through the instigation of Carl Sagan, was to turn around and with its imaging cameras take a picture of our solar system and our world. And so this is a montage of the snapshots that Voyager took on its way out. You can see Venus, you can see Jupiter, Saturn, Uranus, and Neptune. And this is the image that inspired Sagan to write that very famous book called The Pale Blue Dot. That's us. A single pixel on a CCD camera, on a spacecraft bound for the stars. And so what we have to do is take our experiences within our own solar system and what we know about our own planets. The very famous solar system portrait that was created in 2007 after we had visited a large number of these worlds with spacecraft is take those ideas and go off and begin a hunt for exoplanets that in the back of our mind, many of us had said, it would be kind of lonely that on the third rock from the sun, that would be it. Are there other worlds out there? And if so, what do we want to know about them? And so there's a number of broad questions that I hope to briefly touch upon tonight. Talk a little bit to you about this issue of exoplanet demographics. What is the frequency of planets as a function of their separation from their host star? We have some idea what goes on in our own solar system, but is that common? And what should we expect in terms of the mass of the planets that we find? Should they replicate what we see in our own solar system, where we have small rocky worlds and large ice or gas balls in the outer part of the solar system? So what is the census of the planets that we have out there? And when we find these objects, how are we going to characterize them? What are the properties of these individual exoplanets? How do those properties vary among the diverse set that we find? And you might ask, well, what is the $64,000 question? I think the $64,000 question that's lurking out there and certainly driving a lot of what we do is an answer to a very fundamental question. And that fundamental question is the following, and I posit it to you this way. Are Earth-like planets rare? Because if they are rare, that has certain, I would say, scientific and philosophical implications. But if they are in abundance, that has some different scientific and philosophical implications. And so what I hope to do is sort of lead you through this exercise about where our knowledge has been, how it is developed, and how astronomers like myself, and perhaps even those of you in the audience that participate as citizen scientists in these ever-growing databases, contribute to this exploration of the cosmos, to be an Epicurean, to question whether these worlds exist. Well, how do we go about doing this? Well, the techniques of a modern astrophysicist is one of being a detective. We use fingerprints from the stars to tell us whether or not those particular stars harbor planetary systems. And how do we do that? Well, we use light. We use the fingerprint of light, its colors, its absorption spectra, its intensity, to try to understand what those objects that look like single points of light when we look at the jewel box cluster, what they harbor, what they hide. Now, I'm going to talk about a number of common techniques that are used to discover exoplanets that modern astrophysicists use. There's 4 common techniques, including the radial velocity technique, the transit technique, there's a microlensing technique, and there's a direct method of detection of exoplanets. I'm going to talk about 3 of the 4, 2 of which we are directly involved with here in projects at the Institute for Astrophysics, and 1 for context that has really sort of blown open this field into a real exciting area. And I won't talk so much about microlensing. That's kind of an interesting discussion about massive objects, and perhaps we'll have a public lecture about black holes and supermassive objects and the influence of the space-time around them. So I'm going to concentrate on the upper 2 and then direct imaging, because that's where, in some sense, we have made great strides over the last 10 to 20 years. Now, the first type of detection method, or our being Sherlock Holmes with our little glasses out there trying to understand the crime scene from the fingerprint of the light, is what we call the radial velocity technique. And this is kind of an interesting little technique, and it can be more or less summed up by the following. If I look at a star out there, it looks like a single point of light, but if I take its light and I disperse the light into a spectrum, into its colors, something very interesting happens due to the gravitational dance that that star does if it has a planet orbiting about it. And the way this works is as follows. If I look at the light from the star and disperse it, and this is an optical spectrum here from the blue to the red, as the planet, the unseen world, orbits about the star which I can see, it slightly tugs on that planet as it's going in its orbit. And so what you see is the star and the planet are doing a dance. And we're measuring the light from the star in the spectrum, and the fingerprint that we see oscillates back and forth due to the fact that the star is moving away from us, and then the star is moving towards us as it's being gravitationally tugged by that unseen planet. This particular technique is called the Doppler effect. You often experience this by sitting in your car as the train is coming by the crossing. You hear the horn of the engineer signaling, "Don't cross." The pitch goes up as the train approaches you, and then the pitch goes down. It's an example of a Doppler effect. Well, we can do the same thing and watch this periodic oscillation of lines in the spectrum, these dark lines, oscillating back and forth and back and forth and back and forth. Think of somebody on a swing. And you push the person on the swing, and they oscillate away from you, and then they come towards you, and away from you, and then they come towards you in a nice regular pattern. And we can measure what we call the velocity of motion as that object is moving towards us and away from us, and towards us and away from us. It's a nice harmonic motion. And so what we do is look at certain stars, and this is an example of one of the first objects detected with this technique by Mayer and Quizal, looking at a sun-like star. Why would we look at a sun-like star? Well, out of the millions of stars that are out there, why don't we start our search by looking at stars that are similar to our own sun? It's a pretty logical thing to do, given that, at least in our limited experience in our solar system, we can find planets of all shapes and sizes, and on one of those planets, things have potentially been correct enough that life has evolved. So this is what you would find in this radial velocity technique. As the star is moving towards you and away from you, this pattern repeats. So on this axis is what we call the phase, and on this axis is the RMS velocity of the star moving back and forth. And it's a sinusoid. And it takes many, many years to build up these curves. This particular observation of 51 peg B took about 3 years to build up this curve. And I would point out they're trying to measure a velocity relative to no motion, that's what this dotted line here, of roughly 112 miles per hour. In other words, the star was coming towards you at 112 miles per hour and then moving away from you at 112 miles per hour. That star is roughly 51 light years away that you're trying to make this observation on. Now, to put this in perspective, this is kind of interesting. Yes, Chick, there's miles per hour and there's something as phase here. Let's put this into perspective, right? Fastest man on the earth, Usain Bolt, typically crosses the finish line of a 100-meter dash in about 9.5 seconds when he's having a bad day, right? So he is running at about, 10.45 meters per second, in a straight line. Now, the current RV spectrographs that are used, this radial velocity technique spectrographs are sensitive to the wobble motion. In other words, the star is wobbling towards you and the star is wobbling away from you, of motions of about 1 to 3 meters per second. right? So they could see, in some sense, Usain Bolt running down the 100-yard dash. Well, if we're going to try to detect the Earth, looking back at our solar system from a nearby planet, what would the Earth exert in terms of the wobble on our own star? Well, that's of the order of about 9 centimeters per second, or about 0.09 meters per second. Difficult to do with the current generation of spectrographs. The next generation of these spectrographs are likely to achieve resolution such that we can actually detect Earth-mass planets around nearby stars. A very, very interesting and difficult measurement to make. Nonetheless, we are actually constructing one of these devices with our colleagues at Notre Dame. We called it the eye locator for various reasons, and yes, we've talked to Apple about this. Everybody has an eye app for something. It's a diffraction-limited spectrometer that will take light that normally looks like this, all smeared out, condense that light down into a very focused, diffraction-limited spot, allowing us to achieve velocity measurements of the order of 10 centimeters per second or less. So we are on the verge of being able to detect, in principle, Earth-mass planets orbiting around nearby stars with this technique. And as you might imagine, as the years go by, we get better and better and better at using this particular technique. The holy grail for answering that question, are Earth-like planets rare, is predicated on us populating this region of the diagram. This is mass of Earth masses of objects on this axis here, right? So one Earth mass object will be right about there. We have it just within our detection range. We can certainly see a lot more massive objects using this technique, several tens of Jupiter masses. Those are the big gas giants. Yes, those are interesting for a wide variety of reasons. But if we're thinking about Epicurus' statement, we know life has been successful on the Earth, so why don't we look for Earth-like planets? Because those are the ones, at least in our limited experience, are the interesting ones. Those are the ones that we might want to go visit, potentially on vacation. Now, let me turn to another technique. This particular technique has actually been mastered by spacecraft. It's a technique that we can do from the ground, but it requires great stability. And this technique is called the transit technique. And this picture is meant to illustrate how this works. If I'm staring at a star, and there happens to be planetary bodies that are orbiting that star, as the disk of the planet transits across the bright disk of the star, I can measure a change in the star's brightness. So in other words, over time, if I'm watching this particular star, as the unseen planet moves across the disk of the star, the relative amount of light that I measure from that star will dip and then recover, and then dip and then recover over time. And this technique was used actually many hundreds of years ago to establish the size of the solar system by observing the transit of Venus across the disk of our own sun. So this transiting technique relies on making very, very precise measurements of the relative change in the brightness of this star that you see that may or may not have an orbiting planet about it. And this technique was really championed by the Kepler mission. The Kepler mission was designed with very, very sensitive detectors to stare at a fixed region of space above the Northern Cross in Cygnus without blinking for many, many years, and to try to measure hundreds of thousands of stars and what the variation in their brightness might be over time to see if there is any repetitive signal that might indicate that there is a planet orbiting otherwise would have been observed as a dot of light. And the Kepler mission is actually very interesting. I see some of my undergraduate students out in the audience here. One of the principal science investigators on this mission currently was my first undergraduate REU student, doing a research experience in the summer, learning a little bit about astronomy. Now she's out at the edge of the universe doing really cutting-edge stuff. I think that's really cool. It's a really neat story. And the whole story behind the Kepler mission is a mission that kept getting canceled and canceled and canceled by NASA and finally flew on a wing and a prayer. And what has this mission revealed to us? Hundreds and hundreds of exoplanets lie out there in the stars. This is an example of the types of planets that they were detecting. Kepler 4b, 5b, 6b, 7b, 8b. We'll come back to this interesting telephone number system here that astronomers use. They were detecting the transit of planets of various sizes across the disk of their star. And these are some of the light curves, we call them, of the first 5 planets that were discovered through this technique. And the depth of the light curve tells you a lot about how the plane of the orbits of the planets are. And we'll talk a little bit about why transiting planet observations are interesting for another reason, because I can begin to tell you what the atmosphere is on these planets. And indeed, once I know what the atmosphere is like, I could probably tell you, in some sense, maybe what the weather is going to be like on that particular planet. Now, the numbering scheme here, when you begin to get into this exoplanetary game, is rather interesting. And I just grabbed this little NASA video to explain what these things are all about and how they are named. So let me play this for a second here and see if it actually works.
As you probably know, exoplanets can be pretty weird places. Some of them have atmospheres that are torch black or rain made out of molten glass. But do their names have to be so weird too? I mean, they have names like HD 20504b and Kepler 12c. Why can't they be named after cool stuff like Supreme Court justices or members of the Wu-Tang Clan? First of all, there are thousands of exoplanets, so coming up with good names for every single one of them would take a really long time. But more importantly, these names give astronomers really valuable information about each planet. And when you've got thousands of them to sort through, that's pretty helpful. A planet name like Ghostface would be cool, but it doesn't tell you a whole lot. One of the most common exoplanet names is the letters HD, and then a whole string of numbers, and then a lowercase letter. The HD and the number are actually the name of the star that the planet orbits. Astronomers have massive databases of stars, and each one gets a number, so the HD part helps them look up the star's location. The letter at the end tells you in what order the planet was discovered, so the first one gets a B, and then a C, and then on down the alphabet. When a bunch of exoplanets orbiting the same star are discovered all at once, they'll usually be ordered based on their distance from that star. So the closest one will get a B, and then the next one out C, and so on. Now, if later on astronomers find a new planet orbiting the same star, it will get the next unused letter, regardless of where it orbits. Now, you might be wondering, why did the planet start with the letter B? That's because astronomers use a capital A to indicate the star in a solar system, or the brightest star if there's more than one. So in a binary system, the brighter star would get a capital A, the dimmer star would get a capital B, and the first planet would get a lowercase b. Sometimes stars with exoplanets will be named after the mission or the project that discovers them. So planets found by the Kepler mission will start with the word Kepler, and planets that were found by the Corot mission will start with the word Corot. There's been a lot of talk in the scientific community about trying to give exoplanets more interesting names, and it's likely that in the future some of the coolest discoveries, say if we find an exoplanet that we know to be a lot like Earth, those will finally get names that are easier to remember. That's it for this Q&A, Alien. Keep an eye on Planet Quest for the next video in the series and all the news and images you can handle, because exoplanet science never stops.
And really, it never stops. But that gives you some idea of how we name these things once we find them. Now, the other thing that the Kepler mission has done, as this video has suggested, is we now know that there's hundreds of exoplanetary systems out there. Some of those exoplanetary systems have multiple planets in them. And by observing these transits over long periods of time, I can build up an understanding of how those planets orbit their host star. Much the same way that if I watch in the night sky Jupiter move over time, I can get some understanding of how our own planets, the wanderers in our sky, move in their orbit. Once I use the transit of Venus to lay out the size scale. And Kepler mission has a lot of interesting graphics to it, but one of the things I find most fascinating is they made sort of a mechanical model of all the stellar systems that they've discovered, scaled how those planets orbit about their host star in terms of the size of the planet and their relative distance away from their host star, and tried to capture this in a single picture that's animated. So I'm going to play you what is called the mechanical universe of the orbiting objects that Kepler has found. And it's a rather, and I apologize for the music here, but I didn't make this little thing here. What they have done is made an orrery, and what you see here is different planetary systems. The size scale of the orbits about the host star are scaled to the planet size in each system. And what this is meant to show you is our first taste of planetary demographics. The planetary systems come in all shapes and sizes, with all different size scales for orbits, orbital times. We orbit about our sun once every 365 days, but that is not necessarily the norm. And as you look at all these systems here, it's just fascinating to look at the diversity of planetary systems that are out there. Some of these large Jupiter-like objects are so close to their host star that they're being evaporated by the radiation from their host star. Likely those systems do not have terrestrial planets in them, whereas others have more lazy orbits, where the smaller and potentially more rocky bodies are at similar distances to the rocky bodies that we find in our own solar system about their host star. And so maybe those are the ones that we want to look at. And so you can play this over and over and over and over again and watch your favorite planet go round and round in this stylized orbit. But one of the other important things that using this transiting technique allows us to do is actually not only determine the orbit of these particular objects and their size, but to measure their atmosphere. And how does this work? This is another fascinating thing you can do.
Since the early 1990s, astronomers have known that extrasolar planets, or exoplanets, orbit stars light years beyond our own solar system. Because most exoplanets are too far away to be directly imaged, characteristics such as size, composition, and atmospheric makeup must be determined through a variety of indirect methods. For instance, when an exoplanet passes in front of its star, or transits, it blocks a fraction of the star's light and causes a dip in brightness. Large planets block more light, so the size of the dip can be used to determine the size of the planet. By observing an exoplanet's gravitational pull on its star, astronomers can also determine the planet's mass, and thus calculate its density, to see if it is composed of rock, like Earth, or gas, like Saturn. But to fully understand an exoplanet, astronomers must study its atmosphere, and the information that they need is encoded during a transit. As the planet crosses its star, its atmosphere absorbs certain wavelengths of light, or colors, while allowing other wavelengths to pass through. Because each molecule absorbs distinct wavelengths, astronomers spread the star's light into its spectrum of colors to see which wavelengths have been absorbed. The dark absorption bands act as molecular fingerprints, revealing the atmosphere's chemical makeup. Knowing the depth and density of the atmosphere is also important. To figure this out, astronomers observe the transit at many different wavelengths. At wavelengths where more absorption occurs, the planet will appear larger, with the change in size indicating how deeply the atmosphere extends, and its density at different altitudes. Measuring the depth of absorption at each wavelength gives astronomers the planet's transit depth curve, which allows them to model the composition, height, and density of the atmosphere, providing a detailed picture of the planet. Recent studies suggest that exoplanets and their atmospheres come in a wide variety. At one extreme are hot Jupiters like WASP-19b, a boiling gas giant that orbits its star far closer than Mercury orbits our Sun. Visitors who could survive the heat might complain about the air quality. Planet WASP-19b's jagged transit depth curve suggests a deep atmosphere of poisonous hydrocarbons, with methane and hydrogen cyanide far more abundant than water. By contrast, planet Gliese 1214b is a comparatively inviting water world. Its nearly flat transit depth curve hints at a shallow atmosphere of pure steam enveloping an ocean thousands of kilometers deep, with an interior of hot ice, water solidified by extreme pressure rather than cold. As detection methods improve, astronomers will search the atmospheres of Earth-sized planets for signs of life such as water vapor, oxygen, and methane, taking us one step closer to finding a world like our own, all thanks to some flickering starlight.
And indeed, that flickering starlight through the transit technique we'll come back to in a few moments, because with some clever techniques, we can also do that from the ground using direct imagery. Now, one of the things that the Kepler mission has shown us here is that over time, our head count of interesting planetary systems detected through the transit technique has continued to grow. Currently, we're up to roughly about 5,000 planets. And if I plot their orbital period on one axis, how long it takes them to go around their host star, versus their relative size, and this is scaled relative to the Earth's radius here, you can see that there's a wide variety of planetary shapes and sizes. For scale over here, here's the Earth, there is Neptune, there is Jupiter. Now, the real pay dirt is going to come down in this region here. If we're going to answer that fundamental question, are Earths rare, we need to know whether there's a lot of dots in this area or few dots. And indeed, if we want to find an object that's like a mirror Earth, something that looks very similar to our own planet, we need to find a planet of the appropriate mass with the appropriate orbital period at the appropriate distance from its host star to be in what we call the Goldilocks zone. Not too hot, not too cold, just what? Just right. And, of course, then we have to have the right atmosphere. So let's move on to the last technique. Oh, yeah, that's kind of cool. You know, astronomers use these interesting little techniques to measure the motion back and forth, or maybe they're looking at this faint flickering of starlight. Show me a picture, right? A picture is worth 1,000 words. So show me a picture. So I'm going to turn now to a discussion of what we call direct imaging. There are certain systems out there where if I'm clever enough and have a large enough telescope, I can literally take a picture. Pictures are easily interpretable, right? I know an exoplanet when I see it, just like good art. So I'm going to talk a little bit here about the direct imaging technique, something that we do actually all the time at a facility called the Large Binocular Telescope Facility down on Mount Graham, Arizona. This is one of the facilities that the Institute here has access to. And it's a rather interesting telescope. It has two 8.4-meter mirrors on a single mount, so think of this as like the biggest binoculars you could ever get your hands on. I bet you if I stare at certain stars with these high-power binoculars, I can take a direct picture of an exoplanet and not have to worry about spectroscopy and transit depths and everything. I can detect the planets right away. And you might be curious about the ever-ending quest of why astronomers like bigger and bigger and bigger telescopes. In today's world, this is a large telescope, but is by no means the biggest planned telescope in the world. The next generation of telescopes will be of order 20 meters across, the primary. So what is 20 meters? Well, I take 20 meters and multiply it by about 3, so 60 feet across. We're starting to talk about the size of football fields. Big. That is the next generation of telescopes. So why do astronomers like big telescopes? Well, here's the Hubble primary mirror. It's about 2 meters across. Here's the James Webb Space Telescope, the next large space telescope that will launch into space. It's roughly about 6 meters across. And the whole reason astronomers like bigger and bigger telescopes can be boiled down into two things. One, I have a bigger light bucket, so I can detect fainter sources, and planets are illuminated by their host star. They reflect that light. They're fairly dim compared to the brightness of their star. So I need to have a system that allows me to detect very faint sources. So that's one reason. And the second reason is to improve what I call the spatial resolution. Obviously, these objects are very far away. And so the distance that I perceive that planet away from the host star is very small. So by increasing the size of what we call my aperture here, I can increase the amount of light that I collect, and it goes as some high power, the square power of the diameter of the collecting area. And the spatial resolution scales as the wavelength of light that I'm using to make the observation divided by the size of the telescope that I use. So if I fix the wavelength of light, say I'm going to conduct this study in the optical and get a bigger and bigger and bigger and bigger and bigger telescope here, my ability to resolve points of light gets better and better and better. If I have a small telescope like Galileo had, I can barely resolve the Galilean satellites around Jupiter. That small 3-inch telescope is going to do me no good to try to detect exoplanets directly around stars that are light years away. I need a bigger telescope. No, so that's one reason that we like larger telescopes. And let me come back to this idea of the spatial resolution. Because a telescope like the LBT and the next generations of telescopes that will be even twice to maybe 3 times as large, that are all under construction right at the moment, will be able to split hairs. And what do I mean by splitting hairs? Well, when I look out onto the night sky, I'm looking at a projection of a spherical surface in 2 dimensions. And so in order to measure distances between objects that I see in the sky, I have to measure their angular separation. And so astronomers do this here by dividing up a circle into various smaller slices of the pie. And so we can go from degrees down to minutes, down to seconds of arc by ever so greatly refining the small piece of the pie that we're cutting out when we make this observation. Now, to put this into perspective, a second of arc that you'll see quite frequently illustrated in the next few slides here is about 3,600th of a degree. And so I'm taking a little slice here of a circle and trying to measure the angular extent. Big telescopes can measure the separation of 2 objects on the plane of the sky down to milliarc seconds. Well, what does that mean? Well, if I pull out my hair right now, the average diameter of a human hair is about 100 microns. For those of you that have hair, you can try this experiment. Put that in perspective, a grain of table salt that we all can see is about 500 microns. The visibility limit of your naked eye to see tiny objects like bed bugs and gnats and things is about 40 microns. Typical dime that you have in your pocket has a thickness of about 100 microns. So if I take out an average strand of human hair, say it's about 100 microns in diameter, and I held that at a distance of roughly 21 meters away from me, that human hair would subtend a little angle on the sky of about 1 second of arc. Now, if I take that same piece of human hair and walk about 12 miles away from you and ask you, can you see what I'm holding there? Well, you need a pretty large telescope because the angular extent of that human hair is now on the order of 1 milliarc second. Very, very small angle. At the distance of roughly 3/10 of a light year away, if I tried to take a picture of the Earth would subtend about 1 milliarc second of spatial extent on the sky. So imaging planets is a real problem. They're small objects, they're far away. I need to have good spatial resolution. And so therefore, I need a very large telescope. But that's not the entire problem. Because if I think about the night sky, on a typical clear night, not like today in Minnesota where it's been rainy, and I sit out there and I look at the stars. What do stars do from the ground? Well, they twinkle, right? Everybody knows that nursery rhyme, right? We could all sing it. Twinkle, twinkle, little star. They're scintillating. They're moving around. Oh, that's a big problem, because I'm trying to measure this very tiny dot very far away, but the light that I'm trying to measure it from is dancing all around. It's going to blur out my image no matter how large, in principle, I make my telescope. The atmosphere is a real problem. Yeah, I could go to space, like the Hubble Space Telescope, but that's real expensive. And I can't change the instruments to get a better picture if I come out with the next version of my smartphone that has a bigger sensor on it, for instance, right? So we have a big problem here from the surface of the Earth in direct imaging of planets. We have to get rid of the twinkle. But astronomers have devised a very interesting technique to do that. Suppose here I could design a device that would eliminate the twinkle of the atmosphere. That would allow me to achieve these necessary spatial resolutions to find these exoplanets and take direct pictures. Well, we actually do have a technique, and it's used on the LBT. It's used on most large telescopes. It's called adaptive optics. As the starlight is coming down, the starlight is moving all around due to atmospheric turbulence and changes in temperature and changes in pressure. So what I will see when I try to image an object with a large telescope is the following. The starlight will come down, and I run it through a little device that goes to some sort of sensor, and I see something like this popping up on the screen. There goes the light. Not a very tight image, right? Very blurry, dancing all around. Suppose I could design a device to correct for that. Well, I can actually do that if I split the light that's coming down that looks like a bent-up potato chip through some sort of system here that senses the curvature of the potato chip and then moves a rubber mirror to be in the opposite curvature of the incoming potato chip. I can flatten the light out. So instead of ruffles, I've got Pringles. Pringles stack in a can, right? They make a nice, sharp image because all the light arrives at the same time on my sensor. And what happens when I apply that technique? Well, the image of the object goes like that. Nice and sharp. This is called adaptive optics. It works using rubber mirrors driven at acoustic frequencies, using fast computers that try to sense the change of the wave shape of the potato chip coming in and try to turn it into a Pringle by making the telescope optic bend in the opposite direction. For those of you that approach my age and can't see so well, you might think of getting LASIK sometimes. It's the exact technique that they use to do the high order correction on your eyes, just kind of in reverse. Now, how is this done? Well, what you do is you take part of your telescope optics and you glue a bunch of little magnetic hockey pucks on the back of this thing. And this is an example of the LBT adaptive secondary. This is the actual reflective part of the surface down here. We have hockey pucks mounted there, and it mates to an assembly here. And what I can do in each one of these hockey pucks is apply a little push or a pull on the optical surface in response to the computer telling me I need to flatten out the potato chip into a Pringle. For those of you that have ever worn soft contacts, you've experienced this problem, right? You're going to put it in your eye, and the contact goes flop. These things are very thin. They're only about a few millimeters thick, and they will flop, save for the force that we apply on these magnets, and this allows us to drive this primary mirror, and the shape here is actually pretty, how do I want to say this? The size scale of this is actually not accurately depicted in this particular image. The size of that primary, secondary mirror is about 1 meter across. It's about this big. So it's a large piece of optic that we flex like a piece of rubber to flatten out the light. And we have two of these on each side of the telescope. One on the left side, one on the right side. And we can use that technique and the two large mirrors to actually double our footprint, to make an even larger telescope, one that essentially combines the light of the 8.4 meter mirrors into a single aperture that's 22 meters or so across, right here, by combining the light from this telescope and this telescope to give us an even larger telescope for the price of two smaller telescopes and a little bit of software. And this is one of the interesting techniques that we use at the LBT to take direct pictures of exoplanets. How do we do that? Well, we built a little device here that takes the light from one side of the telescope and light from the other side of the telescope and combines that light into a single image. So this is what we call the Large Binocular Telescope Interferometer. This particular instrument here is the sensor that senses the light. It's called ElmerCam. It was built in part here by students and faculty at the University of Minnesota. And it allows us here to take direct pictures of exoplanets. And we've actually embarked upon an interesting little survey called the Leech Survey. And what the Leech Survey stands for is the LBTI Exozodi Exoplanet Common Hunt. We spend a long time sitting around thinking about, geez, let's come up with a funky name. It's an international consortium whose goal is to discover new exoplanets by taking direct pictures, characterize their atmosphere so we can put the habitable ones in one bin and the ones that are not so nice in the other bin, look at the architecture of these systems, would they be stable for billions of years, and establish the meaningful constraints on the prevalence of what we call wide separation exoplanets. In other words, exoplanets that are large and massive that are orbiting out in our own solar system at the orbit of Pluto, which I'll come back to in a moment. Now, this is a very intensive survey. There's going to be 200 targets that we're going to be studying. It takes about 4 years to build up the database, to get all the observations, to begin to say something definitive. But nonetheless, we do have some family pictures at this particular point. Our survey began in February, likely to conclude probably not in 2017, but more like 2018, the best laid plans of mice and men, etc. But we have some nice family portraits. Here is a montage of some of the directly imaged exoplanets that we've been able to attain at the Large Binocular Telescope through this interferometric technique. Now, what you're seeing in many of these images is that the central star, indicated by here, is suppressed by computer processing of the interfered light from both telescopes. And out of that, when we suppress this starlight, we can actually pop out the planet that's orbiting about the host star. This is the size scale, 1 second of arc from the central object. Some of these are only tenths of arc seconds away from their central star. And you can see some of these systems are single systems, some of these systems are multiple systems, and some of these systems have planets that are just at our limit of detectability. We can do a lot of other interesting things with this particular experiment here. We can actually look for disks out of which planets form by directly imaging the material that planets form out of, their disks. We can actually look at objects in our own solar system. I'll come back to this one. This is an image of Io here. Io is the most volcanically active body in the solar system. It's a moon of Jupiter. And what you're seeing here is our processed image, interferometric image, of the equivalent 23-meter telescope baseline here. Put all back together, each one of these circles is a volcanic eruption on the surface of Io. The bright one here is Pele. And to put this into perspective, the spatial resolution that we can achieve from the ground at this object out by Jupiter is of the order of 100 to 150 kilometer footprint. So yes, indeed, technology exists to read your license plate from space. We just happen to look outwards. I'll come back to Io a little bit later, because when I go about this search asking myself, which are the interesting objects that I should be studying, certainly Io is one of them. It's extremely volcanically active. Now, what are some of the systems that we studied? I just selected a few out that I thought were kind of nifty to highlight. One of the systems that we've studied is the telephone number is here, HR 8799. This is the Hubble Space Telescope image of it in 1998. And after that image was stuck in the archive, people began to use large telescopes like the LBT and Subaru and Gemini to do this direct imaging of planets. And they said, hey, we actually see something that looks like an orbiting object. How come the Hubble telescope doesn't see it? And the guys scratched their head and they said, well, maybe we should go back and reprocess our images now that we know that those things are there. And so there is that exoplanetary system in the middle frame with some additional processing after the ground-based folks told them, hey, you better go look at your data. And to put that into perspective here, this is the orbit of the exoplanets around 8799 to scale of the relative size of Neptune's orbit about our own sun in the right-hand column over here. So what you see here is that this particular exoplanetary system likely has multiple planets in it, and the size scale of this planetary system is very equivalent to our own solar system in some sense. Well, that's kind of interesting. We've been following this particular system because one of the things that we're kind of curious about is how each one of these planets moves in its orbit about its host star. Are those orbits stable? Or are these planets bound to spiral into the host star and disappear? This is one of our Elmercam images at 3 microns. We work in the infrared where we're detecting the heat radiation from these particular planets here. 20 astronomical units, or 5/10 of an arcsecond, spatial size scale. 20 astronomical units. What's an astronomical unit? It's the average Earth-Sun distance in our own solar system. We clearly see 4 planets. This particular star is in a system that's 130 light years from Earth towards the constellation Pegasus, the big box in the night sky. Well, why is that interesting? Well, over time, we take all the observations that we have and we try to model what their orbits are. Are these orbits circular-like orbits? Are they elliptical? Are they stable? And this just shows you one of these orbital solutions for planet E that was actually debated about for a long time. Is that really an object? It's not quite clear from the Hubble Space Telescope image. Is that object in a stable orbit? We don't quite know. Now we're beginning to understand, and those are all the data points there, not only from our observations, but other people's observations, to be able to fit the orbital curve of that particular object. Because once we can fit that orbit, we can figure out its mass. So that's an example of the things that you can do with direct imaging, but we can also do something else very nifty with direct imaging. You remember back in that transiting exoplanet example, we can determine what the atmosphere of the planet is. We can do the same thing with direct imaging. All we have to do is take a picture of those exoplanets at different wavelengths. So what we can do here, and those blue boxes are meant to represent the different colors that we would sample in a particular spectrum, we can tell what elements might be present in the atmosphere by looking at the relative brightness of the object in different filters. And to show you an example of this, and this is a fun little example that I always love to do, here's what Jupiter looks like at different colors in the infrared. Now, we all seen Jupiter through a telescope. How many people have seen Jupiter through a telescope? Looks pretty cool, right? You can see that kind of red spot. If you've got a big enough telescope, you can see the moons, the Galilean moons there as little dots. Pretty colorful planet. What happens if we go from the optical and the infrared? Well, if we sample it in narrow filters at different wavelengths, 1 micron, 2 microns, 2.10 microns, 2.27, 3 microns, 3.8. The picture completely changes, right? It looks totally different. What are we looking at here? We're looking at different depths into the planet's atmosphere. And if we combine all of the information that we're getting about where the clouds are deeper, where the clouds are higher, we can understand what are the elements that make up the atmosphere, just from a picture. And so that's what we can do. Here's another object that we've been studying. This object here is called GJ504. And this is the image that was taken from the Subaru telescope. It's an 8-meter telescope on the summit of Mauna Kea here in 2 different colors. One at 1.6 microns, that's indicated in the false color image is orange, and one at 1.2 microns, that's indicated in blue. The central star has been masked out. You see the planetary object up at the top, right? That little dot. For size scale, there is the size of Neptune's orbit on this planetary system. Now, we've also been looking at that particular one. This is our Elmer-Cam image at an even longer wavelength, up by 4 microns. And again, if you think about that Jupiter image, if we look at Jupiter in different colors, we see different depths in the atmosphere. Well, there's our detection of the exoplanet up in that little green box. Very, very faint. So here's what we do. We take our observations, we take Subaru's observations, and we make a little plot. Where is the image of that planet brighter, and where is it dimmer, as a function of wavelength? So we do that. We plot along the bottom axis the wavelength that we're looking at, the color. We plot along the other axis how bright it is. And we have these little red symbols. Then what we do is we run down the hall to the atmospheric scientists that are trying to predict the weather on Earth and say, you got a climate model with various gases in it, like methane and carbon dioxide and water vapor. What would that model look like under various conditions? And they would plot us out a little graph. And then all we do is match the template and find out which is the best model atmosphere for that particular planet based on its colors. So indeed, through direct imaging, I can tell you about the atmosphere of these planets by basically looking at the weather on these planets. So what have we learned? Well, over the course of these various surveys, the number of exoplanets that we detect have been going up and up and up and up. If I kind of extrapolate this curve here, it kind of looks like the famous hockey stick curve, where things tend to infinity. The other thing that's happening is that the number of planets per system keeps growing. There's lots of them out there. There's lots of planetary systems that are multiple. So, have we answered this question yet? Are Earth-like planets rare? Let me spend the last 5 minutes here and chat to you about that. Yeah, are these Earth-like planets rare? Part of this deals with an issue about, in our own solar system, where is the best place to be? Is it on the Earth? Is it on Venus? Is it on Mars? Where is the best place to be? Where is it just right? Well, in part, that depends upon the type of star that we are orbiting. What you see here is the green area is meant to be the Goldilocks zone, or the habitable zone, where planets, if they're Earth-like, would have liquid water on the surface. The hotter stars, that zone is farther out, so maybe Earth-like planets orbit hot stars at the orbit of Neptune, equivalently, in their solar system. Stars like our own sun, they have Earth-like planets that maybe span the orbit between Venus and Mars in our own solar system. Very cool stars might have habitable zones that only extend to the orbit of Mercury in our solar system. So, are Earth-like planets rare? It depends upon which stars you're going to look at. And what does this mean for our understanding of whether Earth-like planets are rare? Well, we have to hunt. We have to find. We have to seek.
If you're the kind of person that pays attention to exoplanet news, and come on, who isn't, then you've probably heard this term before, habitable zone. And you might have noticed that it's kind of a big deal when an exoplanet is found in the habitable zone. So you might be wondering to yourself, what's so special about this zone? Well, one of the biggest goals of exoplanet science is to find another planet like this one. And one really important thing about Earth is that it has a ton of liquid water. In fact, pretty much every living thing we know about needs it to survive. Whether or not an exoplanet could also have liquid water depends a lot on its temperature. Too hot and any water will just boil away. Too cold and the place will be more like a giant snowball. Now, as you might guess, a planet's temperature has a lot to do with how far away from its star it is. A planet that's too close to its star, like Mercury, is just going to bake, whereas one that's too far away, like Neptune, is going to be way too cold. So that sweet spot in the middle, not too hot and not too cold, is exactly where we're looking for another planet like this one. And as you might also guess, where that habitable zone is depends a lot on the size of the star. So it's really close into little dwarf stars and really far away from huge hot ones. So scientists use what they know about stars to calculate a habitable zone for each one. Now, this is something that's really important to understand. When astronomers find an exoplanet in the habitable zone, it doesn't mean it's teeming with aliens. It doesn't mean that it could support life as we know it. It doesn't even mean that it actually has liquid water. All it is a rough ballpark estimate of where liquid water could exist. But if we're going to find another planet like this one, that's probably where it's going to be. Now, keep in mind that there are tons of different factors that affect whether or not life could survive on an exoplanet, like right now, we're really limited in what we can observe. So when you hear about a new exoplanet discovery in the habitable zone, it's probably a good idea to hold off before jumping in your spaceship and heading out there. But we know where to start looking, and as we get better and better at hunting for exoplanets, the stuff we could start to find could change everything.
So, yeah. And why is that interesting? For the following reason. One of the questions that we often ask ourselves is, if we find habitable planets out there that are in the habitability zone, what is the likelihood that those planets harbor life? And if those exoplanets seem to be in abundance in the habitability zone that are Earth-like, after all, that experiment's been pretty successful here on Earth, why haven't we heard from them yet? And this is very interesting, sort of wade into what I would call the alien dilemma. It's the Fermi paradox, first articulated by Enrico Fermi. And basically the question is, where is everybody out there? We now know that exoplanets are fairly frequent. And indeed, we now are in a state where we're detecting many Earth-like planets in the habitability zone around their own stars. There's many answers to the Fermi paradox, one being that maybe we're alone in our part of the galaxy. Or more dramatic still, could we be the only technological society in the universe? After all, E.T. hasn't phoned home yet. Maybe our galaxy is teeming with civilizations, but for some reason, we just don't find them. Or is there obvious proof that we're alone in our part of the galaxy? These are the next level of questions that we will begin to explore now that we know the census of habitable planets and the frequency of planets. It's unlike anything we ever imagined. Now, even in our own solar system, things are getting interesting. You may have seen in today's news, this news flash. This is an image of Pluto, which, by the way, is no longer a planet. It's a minor planet in our solar system. But the New Horizons mission has seen something very interesting. And I just wanted to draw your attention to this. On the flight back from the Large Binocular Telescope on Tuesday, serendipity hit. Alan Stern, who is the project scientist for this particular mission, was sitting in the row ahead of me, and we turned around and had a lively conversation, and he said, wait until this picture comes out, it'll knock your socks off. So let me explain what you're seeing here. You're looking at Pluto, as seen by the spacecraft looking backwards towards the sun, so you're backlighting its atmosphere. And what you see above the limb of the planet is a very extensive, dense nitrogen atmosphere, extending hundreds of miles above this body's surface. Totally unexpected. Totally mind-blowing. Because in our own solar system, where is the only other atmosphere that's nitrogen-rich? The Earth. The other interesting thing about this image, you can see large mountain ranges, you can see smooth, flat areas. What you're looking at is actually apparent fluid flow across the surface of Pluto, caused primarily by the movement of nitrogen as a fluid. Well, that's a hydrological system, just like the Earth has rain. There's other places in our solar system like Titan and Enceladus that have liquid water in one case, and in the other case, flowing hydrology systems of methane, which I can just substitute in for water in many biological systems and get the same sort of things to run. So, this idea of a habitable zone, we need to think a little bit about. It's not just too hot, not just too cold. It just might be everywhere. And again, here's another interesting thing. With these techniques that we use at the Large Binocular Telescope, we can make all sorts of interesting observations. What you're seeing here is the eclipse of Io by Enceladus, as seen from the ground in February, by Europa in February. And you're seeing one hotspot volcano and another hotspot volcano that just erupted. There goes the limb of Europa across. And we recapture the fringes as the transit occurs on the other side. The interesting thing about this is we will have spatial footprint resolution when we work on this data of the order of 10 meters. And so I can tell you how big the lava lake is around Pele, and I can tell you how that lava sloshes around the caldera of Pele without ever leaving the surface of our planet. The possibilities are endless, and I'd just like to leave you with another fascinating image. Everybody recognize this beast? Saturn, right? It's Saturn. And this is another interesting photograph of Saturn. It was taken by the Cassini spacecraft as it flew on the backside of Saturn, looking back towards the sun, so it's backlit. And you see the nice disk of the planet. You see the rings. You see all this fuzzy little stuff, which is actually tiny little dust particles that are levitated like static electricity above the ring system in a chaotic orbit. The ring system on Saturn is transitory. If it wasn't repopulated by new particles, it would disappear in the order of a few 100,000 years. There's some other artifacts in this image, and unfortunately, let me see if my laser pointer is still alive here for the last 30 seconds. Go. Let me point out some interesting things there and 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 there. Just bad sensor. Well, one of these is actually very interesting. This dot here is interesting. So I've cut it out and I've blown it up. Do you know what you're looking at? The Earth. How do I know it's the Earth? Well, camera, it looks like it's out of focus, right? There's this little tadpole right up over there. That's the moon, orbiting the Earth. We didn't have quite the spatial resolution to clearly resolve them. That's why the image looks like a little tadpole. That's us. Now we're looking out, potentially looking for them, right? So the world of exoplanets is exciting. There's a lot of interesting science in it, a lot of interesting atmospheric chemistry, a lot of interesting philosophy. But I would posit to you that we're on the cusp of finding hundreds of Earth-like planets orbiting other stars. It will no longer become a discovery exercise. It will become a characterization exercise. It will become the hunt for life out there, in earnest, in your lifetime. And I would just end with a few readings. If you're curious about where to go after this, play some mood music. I'd encourage you to pick up 5 Billion Years of Solitude. It's very interesting read about exoplanets. Mere Earth, which is a discussion of, what are we really looking for when we want to find some planet that's like our own. Strange New Worlds by Ray J is a nice little read about, what keeps astronomers up at night searching for exoplanets. And Castings wrote a fascinating book that's a little bit deeper called How to Find a Habitable Planet. You can follow our planet hunting by going to the LBT blog site here and following the posts that we put up, or you could follow various advances in NASA exoplanet science at NextSci. That's the LBT on a bright blue lit day. That's the gopher. That's what we're hunting for. I encourage you to become curious. I encourage you to join us on this journey. And just think about the expanse of the cosmos. Thank you, and good evening. So the question is there a preferred rotation axis of these exoplanets about their host stars? We can't really do that right now. We know in our own solar system that there are some planets that have retrograde rotation, like Venus, very slow. Other ones that have their rotation axis knocked into the plane of their orbital plane about the sun, like Uranus. What caused that? Probably collisions of some sort. With the exoplanetary systems, we can't do that yet. We might be able to get some idea of the rotation axis of an exoplanet by studying the change in the cloud structure in the exoplanets. It's a little bit TBD, but we're working on that in GJ504b, actually, because we can accumulate these observations and look at the change in the atmosphere. And one of the things that changes the atmospheric curve is the presence or absence of clouds. Okay. You ever play with Play-Doh? Right? You take Play-Doh out of the can, it's usually hard, and then to get it malleable so you can put it on comics, you put your hands in it, you squeeze it, right? You rub it around. Io is undergoing the same effect. It orbits so close to Jupiter, which is a very massive planet, that it's being tidally stressed. It's being squeezed, it's being relaxed. It keeps the interior of that planet fluid. Now, the volcanism that we see on Io is unlike the volcanism that we see here on the Earth. If you go out to Hawaii, you go to Italy, for instance, you're looking at basaltic magma that has a lot of silicon in it, beach sand. On Io, what you're looking at is sulfur. Volcanoes made out of sulfur. And so that's essentially why Io is so active. One of the puzzling things about Pluto, it also seems to be tectonically active. There are images, and that image that I showed you, that are very smooth. They look like they've been resurfaced. There are mountain ranges. How do we get mountain ranges on the Earth? We have plates colliding. How do you get mountain ranges on Pluto? A very small object. It's orbited by Charon. It's way out in the outer part of the solar system. Maybe you will be able to tell me the answer in a few years. Because right now, all I can do is say, wow, that's really cool. Sure, one of the other things that Kepler has done is only looked at a limited volume of space, right? It's only that tiny footprint. And so what we're also doing is in the process of the iLocator design, Justin Krepp is the team lead, is also one of the scientists on the next planet-finding mission to be launched by NASA called TESS, the Terrestrial Exoplanet Survey Satellite. Now, it will try to improve upon those statistics about what we find in the transiting environment, but we need to combine that data set with a radial velocity data set because they provide complementary data in some areas and new data in other areas. And we might be able to sort that problem out. We just don't have enough statistics currently. The direct imaging of exoplanets also in some senses, a little bit biased. It depends upon how you're looking at the picture seen from the Earth. If all the planets are orbiting face on, you can detect all of them. If they're orbiting edge on to your line of sight, it's like the Galilean moons, right? The Galilean moons, when you look at them, and I think Jupiter's up in the morning and not in the evening, so we won't see it tonight, they move in a fixed pattern around Jupiter. And this is what Galileo discovered that sort of blew our whole mind about the solar system initially, right? There's other worlds orbiting about Jupiter. How can we be, something that's more self-centered in some sense? But we're working on that. Sure. James Webb Telescope is slated to launch hell or high water in December of 2018. Yes, it will fly. Whether it's ready or not, we've been told this. It's a large aperture telescope. It will be involved in the hunt for exoplanets also. Because of its large atmosphere, and now it's above the atmosphere, it doesn't have to apply some of these fancy techniques that we use on the ground. It will also be engaged in this hunt. They will have spectrometers that can also measure atmospheric signatures of exoplanets. So one of its other missions is to pursue exoplanet science. However, there is another mission that's on the books called WFIRST, and Claudia Scarlato, who's a member of our institute, is involved with that one, who's one of its prime science directives is also to find exoplanets. So there's a whole slew of these spacecraft that are going to be launched because it's kind of a grand, curious challenge now to us, right? We've whetted our appetite from our current census. What does the future hold for us? So the James Webb Telescope will be involved in that. There's members of our faculty here at the Institute that are intimately involved in the planning of that particular mission. In fact, my team here is working on cometary science, and the reason for that is we're interested in how comets influence the evolution of life in exoplanetary systems by bringing to those systems water, by bringing to those planets organic material. Yes, there is a big telescope, the GSMT, the Giant Segmented Magellan Telescope. And its concept is sort of like the LBT on steroids. Instead of having two 8.4 meter mirrors, you have 7 arranged in a pentagram on a single mount. Now they're actually casting those mirrors underneath the football stadium at the University of Arizona. Not on football weekends because the vibrations are too much with the cheering crowd, but when the football team leaves, they have a giant oven. And they've cast 4 of those mirrors. That's one concept that is now being actively pursued in the United States through a consortium of universities and other philanthropic donations. There's a second U.S. telescope being built called the TMT, or the 30-meter telescope. The acronyms keep changing faster than exoplanet telephone numbers here. That is the Keck telescope on steroids. So in other words, you take this hexagon segmented telescope and you scale it up to an aperture of 20 meters. 2 competing telescope exercises in the United States. The TMT is primarily led by Caltech. China is involved, India is involved, et cetera. These are very, very expensive things. And not to be outdone, the Europeans have their own project that's going on in Chile. So probably by the year 2023 to 2025, you will see 3 super large gargantuan telescopes involved in the hunt for exoplanets. And astrophysics at that point is reaching machines that are probably bigger than we can actually support fiscally or intellectually. I mean, they just become massive. So we have to use some other techniques to probe farther and deeper, not only in the field of exoplanets, but also in the field of cosmology and black holes and all the other fun things that go bump in the night sky are useful for these particular facilities. Yes? Oh, well, there are some sensors that actually use digital signal processors in what we call things like Shark Hartman sensors. It's sort of pyramid sensors. We break the light up into little different pieces, and we do use some digital signal processing there. The computational algorithms that are used in this reconstruction of the wavefront are very, very computer intensive. There's small little DSP boards, digital signal processing boards, that sit right there, and they put out a lot of heat, and it's actually rather an interesting assembly to see working. So it's also, for those of you who are thinking, well, I'm not really into astronomy. Maybe I'm into computers or technology. I mean, all these large telescopes require excellence in electrical engineering. They require excellence in computers. They require excellence in coding and signal processing and optics. I mean, you have to really be a neat jack of all trades to pull all of this together to do some of this. And in fact, another interesting telescope that's being built in Chile that will complement the GSMT is the Large Synoptic Survey Telescope. It's a telescope that's designed to study the night sky in 6 colors, measure the entire night sky in 6 colors once a week, in part to look for transiting exoplanets, but in part just to catalog what's out there. It will be producing petabytes of data a night to be handled by our favorite friends, Google, because Google is very good at figuring out data streams, right? They know what you want to buy the next day. They're going to tell the astronomers what you want to look at the next day, right? You get the push ad on your iPhone.
All right. First of all, let's thank Chick again for this wonderful talk.